Welcome everyone. I am Mahdi Bahmani. Today we are diving into one of the most transformative technologies in modern software engineering, Docker. If you have ever dealt with the dependency hell of a project that works on your laptop but crashes in production, you have felt the exact pain point. Docker was built to solve. Docker didn't just give us a new tool, it fundamentally changed the industry standard for how we package, ship, and scale software through OS level virtualization. By the end of this course, you won't just talk about the theory. We are going to deconstruct the Docker architecture, settle the containers vs VMs debate once and for all, and move into the hands-on Docker workflow. You will leave here not just knowing what a container is, but knowing exactly how to build, run, and manage your own. Let's dive in. By the end of this session, we will have moved beyond just basic definitions to a deep practical understanding of the Docker ecosystem. We will start by defining containerization and revisiting the historical dependency hell, the very problem Docker was engineered to solve. From there, we will deconstruct the Docker architecture, looking under the hood at how the client, daemon, and registry interact at the brain of the system. To get the most out of our hands-on labs, you should have a baseline comfort with the Linux command line, especially the skills covered in an LPIC 1 or similar certification. Since Docker is natively a Linux-based technology, understanding how to navigate the file system and manage permissions will be our secret weapon. One of our key goals is to settle the debate between containers and virtual machines, helping you make high-level architectural decisions in your professional projects. Then, we will get hands-on with the core Docker workflow, mastering the pipeline from Docker file to image to running container. Finally, we will explore real-world use cases and industry best practices. I won't leave you hanging. I'll be laying out a comprehensive Docker learning roadmap so you know exactly what to practice tomorrow, next week, and next month to achieve true mastery. Course prerequisites and environment setup. Before we dive into the world of containers, we need to make sure our foundation is solid. Think of this slide as the pre-flight checklist. First, you need to be comfortable in the Linux terminal. We won't be using a mouse to manage Docker. We will be using Bash. If you know how to move through folders, create files, and use pipes, you are in good shape. We especially lean on the LPIC 1 standard here if you understand the Linux philosophy where everything is a file. Docker's configuration and volume mapping will make much more sense to you. Second, we are going to be installing a lot of software. You should be familiar with your package manager, whether that's apt on Debian or DNF on Rocky Linux. If you have ever installed a Postgres database, MySQL database, or a Node.js environment via the command line, you have the skill we need. Regarding networking, Docker is especially networking in a box. You don't need to be a Cisco engineer, but you should understand what a port is and how an IP addresses works. The virtual lab. Finally, let's talk about your lab environment. We will be working inside virtual machines using VMware or VirtualBox. Pro tip for the lab. Once you have your Debian or Rocky Linux OS installed and updated, stop. Take a snapshot immediately. Label it clean install. This is your undo button. If we break the network stack or mess up the Docker daemon later, you can revert to this clean state in seconds rather than spending an hour reinstalling the operating system. We do have our VMs ready and our snapshots taken. If so, let's move out. What is Docker? Docker is a platform that allows developers to package applications and their dependencies into a standardized units called containers. These containers can run consistently across different environments, whether on a developer's laptop, a test server, or in production. Think of a Docker as a way to bundle everything your app needs: code, runtime, libraries, system tools into a single portable package that behaves the same everywhere. Interactive exercise 1: the Hello World. Let's get our hands dirty. If you don't have installed Docker yet, don't worry, I will explain a step-by-step installation in the future sessions. You could also follow instruction of install from my website. Open your terminal and type docker run hello world. Watch the output carefully. Notice how Docker first looks for the image on your machine. When it doesn't find it, it goes to the internet to pull it. That message you see on your screen didn't come from your computer. It came from a tiny, isolated environment running inside a container that lived for just a fraction of a second. Look at this message. To generate this message, Docker took the following steps. Number 1, the Docker client contact the Docker daemon. Number 2, the Docker daemon pulled the hello world image from the Docker hub. Number 3, the Docker daemon created a new container from that image which runs the executable that produces the output you are currently reading. Number 4, the Docker daemon streamed that output to the Docker client which sent it to your terminal. The problem works on my machine. Before 2030, developing software was often a nightmare. Think about it, you develop on a Mac, the test server is running Ubuntu, and production is on Red Hat. You have Python 3.9 locally, but the server has 3.7. Suddenly, the app crashes. This is the matrix of doom. Docker was created in 2030 by Solomon Hykes at Docker Inc. to solve this by creating a standardized envelope for your code. If it works in the container on your laptop, it will work in that same container on a massive server in the cloud. Why do we need Docker? Because environment inconsistency is the silent killer of productivity. We have all been there. A developer writes code on Mac OS, but it fails on a Linux production server because a specific library version is missing. Docker eliminates this friction. By ensuring the environment is baked into the container, we move from it works on my machine to it works because it's in a container. This reduces setup time for new developers from days to minutes. Docker solves this by ensuring environment consistency, making applications portable, simplifying development and scaling, reducing setup time for new developers. High-level architecture. Docker follows a client-server architecture. When you type a command line docker run, you run the client. Your command travels to the Docker daemon, which is the engine running on your computer or server. The daemon checks if you have the blueprint called an image. If you don't, it reaches out to a registry like Docker Hub to download it. Think of the daemon as the foreman at a construction site and the CLI as the architect giving orders. Core Docker components. Now let's break down the essential components that make Docker work. First, we have the Docker engine. This is the core runtime, the actual engine under the hood that builds and runs your containers. It has two main parts: the Docker daemon, which is the server running in the background, managing everything like a foreman, and the Docker CLI, the client tool we use to send commands. Next are Docker images. These are the read-only templates or blueprints used to create containers. They contain your application code, its dependencies, and everything needed to run. We built these using a text file called a Docker file. You see an example here for a Node.js application specifying the base image, working directory, and commands to run. When we actually run an image, it becomes a Docker container. This is a living, breathing, isolating instance. Containers are incredibly lightweight because they share the host operating system's kernel, unlike virtual machines. Finally, Docker registries. Docker registries are like app stores or warehouses where these images are stored and distributed. The most famous example is Docker Hub, and registries can support both public and private repositories, allowing teams to securely share their own custom images. Images versus containers. This is the most important distinction to learn. An image is a static read-only file. It contains the OS, your code, and the libraries. You cannot change an image once it's built. You have to build a new one. A container, however, is the living, breathing execution of that image. You can start, stop, and delete containers. Using our analogy, the Docker file is the recipe, the image is the prepackaged cake mix, and the container is the cake you are currently eating. Hands-on building your first app. We move from using someone else's image to building our own. Now I'm going to create this Docker file and build the image and then run the container. We use the Docker build command. The "-t" stands for tag, which is just a name for our image. The dot at the end tells Docker to look for the Docker file in our current folder. Once built, this image is now a permanent template on your machine that you can run whenever you want. Let's doing all the steps together. First, I create a folder for my app. Now I create a Docker file. First line from Python 3.9 slim. Second line cmd space upper quotation Python C, and let's call print function hello from the Python container. That's it. Let's check it again. Yeah. Next step is build the image. Docker build -t my Python app, and at the end I want a dot. Look at here, whatever needed my Container is downloading and I have a warning at the end. It's not important actually. Now I can run the container. Hello from the Python container. And now I have two images. The first one is hello world and the second one is my custom images, my Python app. Let's continue. Containers versus virtual machines. Why not just use a virtual machine? Think of it. A VM is like building a whole new house just to use one toaster. It requires a full operating system for every single app, which wastes RAM and CPU. Containers are like an apartment building. They share the foundation, the plumbing, and the heating, the host kernel I mean. But every apartment is private and isolated. This is why you can run hundreds of containers on a single server where you might only fit 5 or 6 VMs. I will also explain in the next session how containers work internally. We will understand key Linux kernel features like namespaces and C groups and confidently compare Docker, LXC containers and virtual machines. Common use cases. Where do we use Docker? It's the backbone of microservices. Instead of one giant app, you run 20 small containers that talk to each other. It's also vital for CI/CD. Your testing server runs the exact same container that will eventually go to production. And if you just want to test a new version of a database like PostgreSQL without polluting your laptop, you can spin it up in a container and delete it when you're done. Advantages, challenges, and limitations. The advantages of Docker are what made it a global standard. First, portability and consistency go hand in hand because the environment is baked in. The container behaves the same on every machine. Second is efficiency. Since containers share the host OS kernel, they use significantly fewer resources than virtual machines, allowing you to run many more apps on the same hardware. Finally, isolation ensures that if one app crashes or has a security vulnerability, it doesn't automatically sync the others. Now, challenges. However, we must be realistic about the challenges. There is a definite learning curve. You have to think differently about how files are saved and how apps talk to each other. Debugging can also be more complex because you are looking into an isolated environment. Additionally, Docker isn't for everything. For example, it's not the best choice for high-end GUI applications. And while Docker is great for one or two containers, if you have 500, you will need an orchestrator like Kubernetes to manage the chaos. It's all about using the right tool for the right job. Interactive exercise. Concept check. Scenario. You have a legacy Windows desktop application with a heavy graphical user interface that requires direct hardware access. Question. Based on the slide, is Docker the best choice for this specific workload? Think of it. No. Reasoning, as noted in the limitations, Docker is not ideal for heavy GUI apps or workloads requiring deep hardware level OS hooks. as it is designed primarily for isolated, portable microservices and web apps. The Docker Learning Roadmap. To close our session, I want to give you a clear map of where to go from here. Learning Docker is like learning a build with Legos. First, you need to understand the individual blocks, and then you learn how to snap them together into a castle. In your first phase, focus on the life of a container. Learn how to start them, stop them, and see what's happening inside. I'm going to learn you whatever you needed in command line. Don't worry about building your own images yet. Just get comfortable with the CLI. In phase 2, you became a creator. You will learn to write Docker files. This is where you learn how to take a raw OS like Ubuntu or Alpine and turn it into a specialized environment for your specific app. Phase 3 and 4 are where the magic happens. You will learn how to save data so your database doesn't reset every time you restart, and how to use Docker Compose to launch a whole fleet of services with one single command. Finally, once you can manage a full application stack on your laptop, you are ready for the final boss of DevOps, Kubernetes. This roadmap is designed to take you from a developer to an architect. Stick to this sequence and you will find that Docker isn't just a tool, but a completely new way of thinking about software. That's enough for now. Great work today. Take a break and we will continue building your skills in the next session. See you then.